This is Colin Selleck of Binghamton University. This video lecture is for the course ME273 Statics, and we use the book Statics by R.C. Hibbeler. Today I'm going to be talking about the moment of a force about a specified axis, chapter 4.5. After today, you will be able to determine the moment of a force about an axis using both a scalar analysis and a vector analysis. First, we'll look at some applications. We'll do the scalar analysis first, followed by the vector analysis, and then we'll solve some problems. First, though, I want to introduce a slide that should have been in last lecture, 4.1 through 4.4. It's how do you take the cross product of like I cross j if you want 2i cross 7j. That's 14, but what is I cross j? Well, you can use this little mnemonic right here. And counterclockwise is positive. That's our convention. So you see this is I, j, and k, and that's positive. So this is a positive k. But what if we wanted to do 3k cross 7j? Well, now we have k cross j is I, but it's going in the minus direction. So this is minus 21 in the I direction. So you can also use a different mnemonic. I use this one, I, j, k, I, j. And when you go to the right, it's positive. When you go to the left, it's negative. So I cross j is k, j cross k is I, k cross I is j. And then backwards, j cross I is minus k, I cross k is minus j, and k cross j is minus I. Okay, let's talk about some applications first. So this sleeve at A, what if it can only hold a maximum resisting moment of 125 Newton meters about the x-axis? How would you determine the maximum magnitude of F before turning about the x-axis occurs? Well, we use the moment of a force about a specified axis. In this case, the specified axis is the x-axis, and we need to take the moment of the force and then find its component along the x direction. But sometimes the moment produced by a force about a specified axis must be determined. So for example, here's a lug nut at O on the car tire, and it needs to be loosened. The force applied to the wrench will create a tendency for the wrench and the nut to rotate about the moment axis passing through O, which you can see here. However, the nut can only rotate about the y-axis. Therefore, to determine the turning effect, only the y component of the moment is needed, and the total moment produced is not important. To determine this component, we can use either a scalar or a vector approach. Now, for the scalar analysis in the case of this lug nut, the moment arm, or the perpendicular distance from the axis to the line of action of the force, is, well, we have this vector r right here, and it's an angle theta from the x-axis. So therefore, the moment about the y-axis will be this moment arm right here times the force. So that would be d sub y. Now d sub y is nothing other than r cosine theta. So therefore, the moment about the y-axis is just f r cosine theta. And you can see that's just a little geometry there. And there's also a moment about the x-axis, right? There's another moment arm here. This is perpendicular to the x-axis. And that would be equal, the moment about the x-axis is f times its moment arm, in this case is r sine of theta. Now, according to the right-hand rule, m sub y is directed along the positive y-axis as shown here. So in general, scalar approach, the moment about any axis is equal to the force in question times the moment arm. That's the perpendicular distance between a point on the line of action of F and point A, and that's not a vector. Now, the vector analysis, which I prefer, To find the moment of this force F about the y-axis, we're going to use a vector analysis now. We must first determine the moment of the force about any point O along the axis, along the y-axis. So you can see that chosen point O right here. And we can do that by applying the equations we've already learned. The moment about O is R cross F. Now the component m sub y along the y-axis is the projection of m sub O onto the y-axis. And it can be found that by using the dot product that we discussed in chapter 2, we can get m sub y is equal to j, unit vector j, dotted with the moment vector. And that's equal to j dot r cross f. We can generalize this approach by letting u sub a be the unit vector along the axis in question. So in this case, AA is the y-axis. So this is the moment of F about a point O on the axis is m sub O is equal to R cross F, you see here. And the projection of this moment onto the A axis is use the dot product. So m sub A is equal, and that's a moment along the A axis, which in this case is coincident with the Y axis, is equal to that unit vector along the AA axis dotted with R cross F. This is referred to as the triple scalar product. It's very useful. We can find now the projection of any moment onto any axis. Now if they're written in Cartesian form, m sub A would be equal to, and now here you can use the determinant method, but instead of ijk across the top, we have the x component of u sub A, the y component of u sub A, and the z component of u sub A. And then it's dotted with R cross F, so this would be R sub x, R sub y, R sub z, and dotted with F. Cross product with F, so we have F sub x, F sub y, F sub z. So you can determine the moment about any axis by using the determinant method by putting in the Cartesian components of the unit vector on the first row, the Cartesian components of the R vector. Now the R vector goes from F to goes from any point along the line of action of F to any point along the line of action of O, or the axis in question actually. And then F sub x is the force being applied. Now when m sub a is evaluated from this equation, it will yield a positive or a negative scalar. The sign of the scalar indicates the sense of the direction of the moment along the a-axis. If it's positive, then the moment along the a-axis will have the same sense or direction as u sub a. Whereas if it is negative, then m sub a will be opposite in direction to u sub a. Once the a-axis is established, point your right-hand thumb in the direction of m sub a, and then the curl of your fingers will indicate the sense of twist about the axis. Providing m sub a is determined, we can then express m sub a as a vector by just multiplying its magnitude times that unit vector in the a direction. So some important points. The moment of a force about a specified axis can be determined provided the perpendicular distance d sub a from the force line of action to the axis can be determined. So in that case, m sub a is equal to the force times that perpendicular distance. If the vector analysis is used, then now this should not be a vector. That is a scalar right there. That's my bad. So the magnitude of the moment is equal to the unit vector along the axis in question dotted with the r cross f vector. Now remember, r goes from any point along the axis A to any point along the line of action of the force F. If m sub a is negative, its direction is opposite that of u sub a. If it's positive, its direction is the same. And if you want the moment vector as a vector, you can take that scalar that you get from this equation and multiply it by the unit vector in the a direction. So let's do some examples. So we have this force F of 200 newtons is applied to the tool as shown. Find the magnitude of the moment of this force about the x-axis. So our plan, we want to use the triple scalar product. And so what that means, we need to find F in Cartesian vector form. And we note that u is equal to 1I in this case because the question was the force about the x-axis, and the unit vector along the x-axis is 1I. And then the vector r in this equation is the position vector from O to A. So as I said earlier, u sub A is equal to 1I. Now we need the r vector. I'm on O and I want to get to A. So in the x direction, I don't have to move in the x direction because everything here is occurring in the yz plane, so it's 0I. And then in the j direction, or y, looks like we need to go a positive 0.3 meters, so it's plus 0.3 j. And in the z direction, looks like we have to go up 0.25, so it's plus 0.25 k. And that is in meters. Now we need to break the force F into its Cartesian components. Well, in this case, it's easy because we are given alpha, beta, gamma. Remember, those are the coordinate direction angles. So to find the component of F, all we need to do is use that formula that we talked about in chapter 2. So the force F as a vector is its magnitude times the, so alpha is from the x-axis, so that would be 120 degrees, so it's cosine 120 in the I, plus cosine of beta. Beta in this case is 60 degrees in the j direction, plus cosine of 45. Beta is 45 in the k direction. So great, now we have everything we need. We can use the equation, m sub x is equal to u sub x dotted with r cross f. And this is a scalar, m sub x. So let's construct our matrix. So m sub x is equal to, now the unit vector is just 1, 0, 0. The r vector is 0I, 0.3j, and 0.25. And the last one is the force. And when you do the multiplication of the force vector from this equation, you get minus 100, 100, and 141.4. Since the j and k components of the unit vector are 0, we only need to cross out the first column and row in this case. So that is equal to 1, this 1, times, and then we're left with this little determinant, 0.3 times 141.4 minus 0.25 times 100. So m sub x comes out to be 17.4 Newton meters. And since it's positive, it's counterclockwise. Let's do another one. Here we have this force F, 30 newtons, is applied to the bracket at A. And we're given it, once again, we're given the direction cosine angle. So finding F in Cartesian form will be simple. We're going to follow the same approach. We're going to find a unit vector along the bracket. We're going to find r of O with respect to A. So I'm on O, I want to get to A, that's this vector here. And finally, we're going to find F in Cartesian form and then use the triple scalar product to solve for the answer. Okay, so we want to know the moment projected onto the AA axis. What is the moment about the AA axis? So we need the unit vector, and looks like that's all in the J direction, right? So U sub A is 0I plus 1J plus 0. Okay. And breaking up the force into its Cartesian components is easy since we're given alpha, beta, gamma. The force magnitude is 30. It's times the cosine of alpha, which is 60 in the I, plus beta was 60 also, so cosine of 60 in the J direction. And gamma was 45, so it's plus cosine of 45 in the K direction. And the last we need is this vector ROA, so we're on O, we want to get to A. So how far does this vector move in the X direction? Well, it looks like it's 100 millimeters, and it's going negative X direction. So R sub OA is equal to minus 0.1. I'm going to do this in meters, and that's in the I direction. In the J direction, we don't have to go anywhere in the Y axis, so that's 0. And in the Z direction, looks like we need to go up 100 plus 50, or 0.15 meters, so plus 0.15. Okay. And that's in meters. Now when you multiply out the force vector from this equation, you get the force is 15I plus 15J plus 21.21. Okay. And that's in newtons. So now we need to find the triple dot product to solve for our answer. And again, that's M sub A is equal to U sub A dotted with ROA cross F. So let's build our determinant, M sub A, or let's build our matrix rather. So across the top is the U vector, and that was 0, 1, 0. And across the second row is the R vector, and that was minus 0.1, 0, and 0.15. And then the last row is the force vector, which is 15, 15, and 21.21. So the moment about the A-axis is now the only one that's going to make a difference here is crossing out the second column in the first row because these are both 0. But remember, on the J direction, you have to put a minus sign. So that minus sign goes here, and that's times minus 0.1, like we're crossing out these two, minus 0.1 times 21.21 minus 0.15 times 15. And when you do that, it comes out to be 4.37 Newton meters. This concludes the lecture on Chapter 4.5, Moment of a Force about a Specified Axis. The next video is Chapter 4.6, Moment of a Couple. See you in cyberspace.